Hello everyone. So today we're going to continue on 13.2. So last few video we get to talk about how to use matrix exponential to solve a system of differential equation, and the main thing to use this method is to obviously to try to calculate the matrix exponential, which is e to ta. So far what we know is that we could calculate e to ta by simply using the definition of what is e to ta, which is basically forming the infinite sum, and then somehow hopefully be able to identify what the infinite sum converges to. Which is not my best way to do it, because it requires you to first having the matrix A having some kind of pattern for its power, and then plug into the power series, and then hopefully be able to identify the power series, what the power series converges to. So there's a lot of difficult things that we have to be able to do in order to actually come up with this matrix exponential e to ta. So we eventually learned that we can actually use eigenvalue and eigenvector to do it, which we write this formula right here on the screen, which is e to ta equal to u lambda sub t u inverse. But of course that also presents a problem. The problem is that if I can actually form matrix U and matrix lambda sub t, and matrix U has an inverse, then I really don't need e to ta, because we already know how to use this to solve a differential equation back in 13.1. So what we want is that we need to be able to calculate e to ta in cases where we cannot use the formula U lambda sub t U inverse. So when would that happen? Well, that would happen when our matrix A has repeated eigenvalue. And that would be where matrix e to ta become useful for us, because all the other previous method that we have learned would not be able to solve the problem. So that's what we're going to try to figure it out. So what we're going to talk about now is the following: is what if, how do we actually calculate e to ta without go through the matrix U and matrix U lambda sub t and U inverse. So the question is, how do we actually compute matrix exponential? In practice, instead of using eigenvalue and eigenvector, is there some way that we can calculate this without getting to either one of those two things? So, of course, there is someone really smart figured it out. So here's the theorem that will allow us to do that, which is called theorem 13.2.3. You will be asked to use this theorem to calculate e to ta on your next test. So make sure you pay attention and know what's going on. So theorem 13.2.3 says the following: an n by n exponential matrix, or actually n by n matrix exponential e to ta can always be reduced to a polynomial of A called P of A, in the form of, and here's the important formula that you need to know: e to ta is always equal to P of A, where P here stands for polynomial of A, and which is equal to summation j from 0 to n minus 1 b sub j of t a to j. Important to identify that the n minus 1 on top, the n is referred to the n by n matrix. Okay, and in this expression, several things are important to for me to point out. Number one, note the following. Note. Number one, This polynomial of A has a degree that is n minus 1. That is extremely important because that will tell me that instead of looking at e to ta as an infinite sum, we can actually rewrite it into a finite polynomial, which is so much better compared to infinite sum, because infinite sum, we first need to know that it would converge, which we know because theorem 13.2.1 states specifically that for any n by n square matrix e to ta would exist, so we know it converges. But the problem is, how do we know what it converges to? And it's an infinite sum, so it's hard for us to actually figure that out. But if it's a finite sum, then we just simply add up all the terms, and because finite, no matter how many terms we're dealing with, we'll eventually be able to finish adding them up and provide an answer, which is a lot better than infinite process, which will never end. 2. In this expression right here, b sub j of t is basically called the coefficient function. And in order to use this polynomial p of a, in order to use p of a to find e to ta, we need to figure out what b sub j of t would be. We need to figure out all the b sub j of t. Because it's not just one of them, because you could have a if n is 2 or 3 or 4, then you have multiple coefficient function, and it might be hard to kind of understand what this expression look like. So maybe give an example. So example is this. This theorem basically claimed that, let's say A is a 3 by 3 matrix. Maybe I should say this. Let's say let A be a 3 by 3 matrix. Matrix. Then what theorem 13.2.3 basically state is this. Then theorem 13.2.3 states that e to ta is actually equal to something like this. Theorem 13.2.3 basically states that I can actually rewrite e to ta by forming a polynomial of matrix A of degree 2, because n minus 1. In this case, A is a 3 by 3 matrix. A polynomials of matrix A of degree 2 in this form. Of course, the problem is we don't know what b of 0, b sub 1, and b sub 2 are. Those are the 3 coefficient functions that we have to figure out to form this matrix, because we do know A. So therefore, we will be able to figure out a to 0, which is 10 to the I, a to first, which is 10 to the a, and a squared would just require me to multiply a by itself, which all these 3 things are something that we can figure it out. So the tricky part is you try to figure out what is b sub 0, b sub 1, and b sub 2. So then the question that you're probably thinking is like, okay, then how are we going to figure out those 3 coefficient functions? Well, that's what the next theorem is for. Okay, theorem 13.2.4. You will almost always use these 2 theorems together because it help you. Theorem 13.2.4 help you figure out what those coefficient functions are, and once you have the coefficient functions, then you can use 13.2.3 to form the matrix e to ta. So what 13.2.4 theorem 13.2.4 state? It states the following: let lambda 1, lambda 2, to lambda n be the eigenvalues of the matrix of the n by n matrix A. Now I know what you're thinking. So thinking like, wait, I thought we were trying to move away from using eigenvalue and eigenvector. No, that's not what I told you. What we tried to figure out is figure out how to deal with when you have a matrix that's repeated eigenvalue. So the fact that we can have repeated eigenvalue can still be something of use. That's what theorem 13.2.4 is going to help us, is that this not only allows us to deal with when we have distinct eigenvalue, which we can technically use the formula right here, u lambda sub t u inverse. But if we do have repeated eigenvalue, now theorem 13.2.4 will now have a way to also deal with that. So therefore, not only it can replace use lambda sub t u inverse formula, but also be able to do something that that formula cannot do. Okay. So let's say this matrix A, which is n by n, have n eigenvalue. Then the coefficient function B sub I guess I can say B sub j of t. B sub j of t in the matrix polynomials from theorems 13.2.3 will satisfy the linear scalar equations, actually functions, scalar equations. So this is not one equation but a whole bunch of equations. The equation will look something like this: e to the t lambda k, lambda j. You know what? I'm going to actually use k because I want to use the index to be j. So I'm going to say e to t lambda sub k would equal to summation j from 0 to n minus 1 b sub j of t lambda sub k to the j, where k go from 1 to 2 dot 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 to n. So if you look at this formula right here, hopefully you recognize that that look almost identical to this formula right here, except that the A and the A, which is the matrix A, get replaced by the eigenvalue. And that's exactly what it is. So now what happened is this would actually form a whole bunch of formula because we are letting k to go from 1 to 2 to 3 all the way to n. So meaning basically you form one of these equations for each one of the eigenvalue that you have. So meaning the following. Oops. That means we have e to t lambda 1 equal to summation j from 0 to n minus 1 b sub j of t of lambda 1 to j. And then we have a second equation for lambda 2. And then this pattern continue on until you go through to the last eigenvalue, which is lambda sub n. Now, if you look at this right here, what do we have here is nothing more than a system of n equations with n unknowns, coefficient functions. B sub 1, B sub 2, dot 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 to B sub n. Actually, technically speaking, actually b sub 0, b sub 1, all the way to b sub n minus 1. Yeah, because the index starts from 0 to n minus 1. And yeah, technically it could go from 1 to n, but then it would require us to put the exponent to be n minus 1. So to make it easier, we start from 0 to n minus 1 so that the exponent can be just what the index is. So that's basically what you try to do. So eventually what happens is when you apply this theorem, you actually end up having a system of equation, and you just have to try to solve for these functions. Now, here comes the important part. What if some of the eigenvalues are repeated? Okay. Now, if some, let's say, m of the eigenvalues, of lambda sub k are equal, are repeated. Let's say, for instance, lambda 1 equal to lambda 2 equal to ... equal to lambda m for that many eigenvalue being repeated. Then what happens is this. Then we have a way to actually help us find the coefficient function. Then the following m minus 1 additional equations will hold true. Must be satisfied also. So now, why is that? Well, the problem is the following. When you have a whole bunch of repeated eigenvalue, what happens is it will basically mean that you have a whole bunch of repeated equation in this system, and therefore reducing your number of equations, but maintain the same unknown functions. So therefore, we need to have new equation to make sure the system would have the same number of equation as the number of unknown coefficient function. Otherwise, you will not be able to solve for the solution that you need. Remember, when you have a system that have fewer equation compared to unknown, you will have infinite solution, which is not what we're looking for. We're looking for a finite, a specific set of coefficient function that will allow us to generate e to ta. So in order to satisfy that, we have to add in extra equation. And in this case would be m minus 1 dimension extra equation, because with m domain of them repeated, one of those out of the m would be the actual equation, while the other m minus 1 domain equation are all repeating the same equation to begin with. So those repeated equations will now go away, and now we have some new equation that we can plug in. So what are these equations? It would be in this form: d to the k over d lambda k e to t lambda sub k is equal to d to k over d lambda k summation j from 0 to n minus 1 b sub j of t lambda sub k to j, for k from 1 to 2 all the way to the last repeating value. So now I know this looks kind of complicated, but it's actually not bad. The idea here is that you basically replace all the repeated equation by higher order derivative of the equation that you have. Now, I know it sounds, m minus 1 actually, because you do need the m1 to be the actual equation. So, it might sound very complicated, but let me show you how to use the theorem, and you'll feel a lot better, because it's, as with a lot of the math formulas that you have learned, try to write out what you try to do is a lot more complicated than actually doing it. So show you how this whole thing works out in an example, and that way hopefully help you see how this whole thing, how to use it correctly. So let's say we're given A to be equal to matrix 1 1 4 1, and with eigenvalue. So we actually use this matrix before. So we know the eigenvalue already. So we're going to just give you the eigenvalue. Lambda 1 is -1 and lambda 2 is 3. I'm going to ask you to go and use theorems 13.2.3 and 13.2.4, and once again you use both of them together to find e to the ta. So how do we actually proceed? So first of all, let's apply theorem 13.2.3. So 13.2.3 basically states the following: e to ta is equal to p of a, which is equal to summation j from 0 to n minus 1 b sub j of t a to the j. For us, a is 2 by 2. Therefore, tell me that n is equal to 2. So, according to 13.2.3, theorem 13.2.3, e to ta would just be equal to summation j from 0 to 2 minus 1, which is 1. B sub j of t, a to j. So what does summation turn out to be? Just become this. B sub 0 of t, a to 0, plus b sub 1 of t, a to the first. Which basically just turn into this. It just basically tells me that e to ta equal to b sub 0 multiplied by the identity matrix plus b sub 1 multiplied by the matrix A. Yes, I dropped the parenthesis t because you just have to remember that b sub 0 and b sub 1 are both function of t. They could also be constant, something constant, but it's more likely that it would be something that involves t in it. So in order to complete this formula, I do need to find out b of 0 and b of 1. So how do we go about doing that? Well, that would be where we use 13.2.4, which basically say that e to t lambda sub k would equal to summation j from 0 to n minus 1 b sub j of t lambda sub k to the j power. So once again, for us, we have k, 1, and 2. And we also have n equal to 2. So for us, we know n equal to 2, and we're going to start with k equal to 1. So therefore, basically meaning e to t lambda 1 equal to summation j from 0 to 1, because 2 minus 1 is 1, b sub j of t lambda 1 to the j. So what does this actually turn into? Well, we know that lambda 1 is, what did I write? -1, so that means e to negative t would equal to, when I plug in 0 over b sub 0 times -1 to the 0 power plus b sub 1 to the -1 to the first power. So -1 to the 0 power is 1, and -1 to the first power is -1. So therefore, this actually results in this equation. So remember, we are basically working off of a system equation. In this case, with a 2 by 2 matrix, we will be working with a system of 2 equation. Now we're going to use k equal to 2, so n equal to 2, k equal to 2. So therefore what I have is e to t lambda 2 equal to summation j from 0 to 1, b sub j of t lambda 2 to the j. So once again, that just becomes e to the lambda 2 is 3. So become e to 3t would equal to b sub 0, 3 to the 0, plus b sub 1, 3 to the first. So therefore, we result in this equation, e to 3t equal to b sub 0 plus 3b1. These two form a system of equation. Therefore, now I can go ahead and try to use that to figure out what b sub 0 and b sub 1 would be. So my first equation is this. My second equation is this. So now what I have to do is basically solve for either b sub 0 or b sub 1. So I'm going to the first thing I'm going to do, I'm going to go solve for b sub 0 first, I guess. I'm going to multiply the first equation by 3. So 3 e to negative t would equal to 3b sub 0 minus 3b sub 1. Second equation, I'm going to keep it exactly the same. And if I now add these two equations together, the 3b sub 1 would cancel out, and therefore combine into 4b sub 0 equal to 3 e to negative t plus e to 3t. And so therefore tell me that b sub 0 or b sub 0 of t would equal to 3 over 4 e to negative t plus 1 over 4 e to 3t. Voila, we just found b sub 0. Now I'm going to do the same thing to find b sub 1. So I'm going to once again start with these two equations. And I could easily plug in b sub 0 and using one of these equations to solve for it. But I'm going to actually do something simple. I'm going to just multiply the top equation by negative 1. And I have negative e to negative t equal to negative b sub 0 plus b sub 1. Bottom equation stays the same. And we'll once again add them together. The b sub 0 cancel out. And now 4b sub 1 would equal to negative e to negative t plus e to 3t. So therefore b sub 1 of t would equal to negative 1/4 e to negative t plus 1/4 e to 3t. Voila! We just found both of our coefficient function. So now we can go back to 13.2.3 and use the formula. So my formula is right here. E to t equal to b sub 0. E to ta equal to b sub 0 times I plus b sub 1 times a. So therefore would equal to b sub 0, which is 3 over 4 e to negative t plus 1/4 e to the 3t, multiplied by the identity matrix for 2 by 2, which is 1, 0, 0, 1, plus b sub 1, which is negative 1/4 e to negative 4 plus 1/4 e to 3t, multiplied by the matrix A, which is 1, 1, 4, 1. And I know you might think like this is extremely complicated, but it's not. Once again, you have to see past all the algebra and understand what you try to do. Here, there are only two terms involved. E to negative t, e to 3t. It's just a matter of trying to figure out what happened to their coefficients. Okay? So, what happened to this? So, let's look at the first corner, which is right here in the top left. The coefficient for e to negative t is 3 over 4 times 1 plus 1, negative 1/4 times 1. So, that would be 3 over 4 minus 1 over 4, which is 1/2 e to negative t. Plus, the coefficient of e to 3t is 1/4 times 1 plus 1/4 times 1, which is 1/2. Let's do the top right. The top right, because it's 0 on the first product, therefore it just basically have negative 1 over 4 e to negative t plus 1/4 e to 3t. On the bottom, it's the same thing because the first matrix is the identity matrix, therefore has a 0. All you have to do is multiply the second b1 by 4, which is negative e to negative t plus e to 3t. The last one, once again, you have to work out the coefficient. So it's 3 over 4 for e to negative t plus negative 1/4. So therefore it will be 1/2 again. And then the coefficient of e to 3t is 1/4 plus 1/4. Therefore is 1/2 again. And that is our e to the ta. Alright, unfortunately it's about 29 minutes already, so I'm going to have to stop here for today. So we're going to continue on with our example on what happens if we have a repeated eigenvalue. Or we have complex eigenvalue. What how does this formula work out. It would work out exactly the same way, and it might actually be a little easier when we do the using complex value, because as you recall, last time we do a complex eigenvalue problem, it took me an entire video, start from here, and took me an entire video, 30 minutes, to go through this example and go through all the algebra to get to this answers right here. Okay, so hopefully using this method would actually make it easier. So we'll see in our next video. Okay, I'll talk to you guys then. Bye bye.